let us continue with our review of scalar vectors and tensors. In physics, the most general way to think about scalars and vectors is the principle that the laws of physics should not depend on the choice of the coordinate systems. How a quantity behaves under coordinate transformation determines whether it is a scalar or a vector or some more complicated object called tensor of higher order. Now, what do I mean by all these things? So, let us illustrate these concepts through an example. Suppose there are two friends S.N. Bose and C.V. Raman, and they are trying to locate a point P, could be the location of a house. So, they are standing at the point O and they want to know the location of point P from O. So, how do and we are assuming in this example that they are inside in a plane. So, there is no z axis, they are in the xy plane for simplicity. So, how do they describe the location of point P from O? So, suppose S.N. Bose, so well what they can do is that S.N. Bose, let us say the first one of them, he will consider this point O where he is standing as the origin and he will draw a coordinate system, let us say the blue coordinate system. So, this is the x axis of the blue coordinate system, this is the y axis of the blue coordinate system, and then he can go from O to A along the x axis and then from A to P, which is parallel to the y axis, then he will reach the point P. So, in his coordinate system he will analyze by writing down that the location of point P from point O can be described by a vector. So, by an arrow. So, the length of this arrow represents the distance from point O to point P, and the direction of this arrow represents the direction in which the point P is located from point O. So, he will write it as an equation, this arrow, this vector, the location, it is called the location or position vector of point P from O as OP, and this can be written as a vector addition of two pieces, one along the x axis and the other along the y axis. So, this is along the x axis, this is along the y axis. Then the length of this vector OA is x and the length of this vector AP is y. So, he will say that the point P, the location is given by these coordinates and these coordinates are x and y. So, two numbers. So, the x component and y component that represents the location of point P. Now, his friend C.V. Raman, he can do the same thing, but suppose that he chooses a different orientation of the coordinate systems. So, he chooses this is the direction of x axis in his choice, which is denoted as the x prime, to make it different from x, the blue one, and we denote this as the red coordinate system. And similarly, this is the y axis of Raman's selected coordinate system, the red coordinate system. Now, in the red coordinate system, he will go along this x axis along OR to a point R, and then he will go from R to P in a direction which is parallel to the y axis of the red coordinate system, and he will reach the same point P. So, again he can denote the position vector of the point P from O by saying is a sum vector as sum of two pieces. So, OR and then RP. So, you can also think of this way. So, you can first go along the y axis, so along OQ, and then in a path which is parallel to the x axis of the red coordinate system, which is QP. So, this is the equation written here. So, this is QP plus OQ. So, from the figure you can see both path you can reach the same point P. So, in Raman system, this length either this or this, which are equal, is the x component of the coordinate of the location of point P, and this represents the y component. So, in Raman system, the coordinates of the same point P are different. So, in Bose system, the point is the coordinates are x y. In Raman system or in the red system, the coordinates are x prime y prime. Now, let us see what is the relation between the coordinates in the blue system and the coordinates in the red system. From this figure, suppose I drop a perpendicular, I draw a perpendicular from A to QP. So, it intersects QP at B. Now, you can see that suppose I want to write down how much is PQ. So, PQ, which is by definition the x prime, is given by the piece QB and the piece BP. So, this is QB plus BP. Now, how much is QB? So, you see that QB, so this QB, so this is a rectangle. So, QB is same as, so let us call this point as M, is same as OM, and if you consider this triangle OMA, in this triangle this is the x, this is 90 degree. So, OM is x cos theta. So, this is x cos theta, hence QB is x cos theta. Now, if you take the other, how much is BP? Consider this triangle ABP. Now, you can easily show by applying geometry that, so the angle between the x axis in the red frame and the x axis in the blue frame for Bose's choice of coordinate system is theta. So, this angle is theta. So, if this angle is theta, then this angle is also theta. This I leave as an exercise, this is easy to show. Now, if this angle is theta, Now, we know that AP represents the y coordinate in the blue system. So, BP is y sin theta. So, this is BP. So, we get an equation that x prime is cos theta times x plus sin theta times y. Now, how much is y prime? So, y prime is this distance. So, y prime is same as OQ, and in this rectangle y prime is same as PR. So, y prime is PR, and PR you can see is same as BM, because this is a rectangle. So, this is BM, and BM is AB minus AM. Now, how much is AB? If I again consider this triangle ABP, we know this AP is y. So, and this angle is theta, then AB must be y cos theta. And if I consider the triangle OAM, in which OA is x and this angle is theta, so AM must be x sin theta. So, I can write y prime as minus sin theta x plus cos theta y. So, I am writing the same equation here, just in a slightly different way, because if you use a matrix notation, so some of you may be familiar with the matrices. So, I can immediately write this in a very beautiful way in using matrix notation. So, I will denote the point P, the coordinates of point P using a matrix column vector with two components. The top component is x, bottom component is y, and the same point P can be written as another column vector x prime and y prime. So, then this geometry shows that there is a relation between the components or coordinates in the red frame, this one, with the coordinates in the blue frame, this one. And so, I can write it as a product of two matrices. So, this represents the coordinates of the point P, the location vector of point P in the blue frame, and this represents the coordinates in the red frame, and this is a product of this matrix which represents all these theta dependent part. So, I can separate the theta dependent part and the coordinate part. Now, let us try to understand what did we do here. So, what we do here is that we know physically that the point P and point O does not, the position of point P and point O are fixed. We consider the same point O, and both S N Bose and C V Raman, they started from the same point O and reached at the same point P. That means that if we want to describe the location of any point on this plane using these coordinates, and if we demand that we can choose any direction as our x axis, then if we take two such set of coordinate system, the coordinates must have some relation from the system, let us say the blue system to red system. In other words, if I want to know, suppose I know the coordinates of the point P in the blue system, and I want to know that what will be the coordinate of the same point P from the same origin O if we choose a different set of coordinate system, that is the red coordinate system, then this is the formula, this is the relation that gives me the new coordinate system. So, how do I go from the blue system to the red system? So, I rotate the blue system, the x axis of the blue system by an angle theta. So, this particular operation, this is called rotation by an angle theta. This is an example of a coordinate transformation. And now, I summarize what we found so far, that if we apply a coordinate transformation, then the location of the same point in two different coordinate system, the coordinates will be different, but they will be related by a particular rule, and this rule is a combination of this cos theta sin theta. So, in 2D this is an example of this rule, and this 2 by 2 matrix which contains the information about how much rotation is required to go from the blue frame to the red frame, this is called the rotation matrix. That represents, this matrix represents this particular coordinate transformation. Now, if we, so this is this particular, that the fact that they are related is the meaning of this statement that the laws of physics should not depend on the choice of coordinate system. In this particular case, what we demanded here is that the position of a point, position vector of a point P from another point O should not depend on the choice of coordinate system. Now, I want to point out, highlight 2 points. Now, if I look at the distance between from point O to point P, so this distance is represented by this length of this side OP, and this OP square is equal to OA square plus AP square. So, OA square is x square and AP square is y square. Now, the same distance OP can be also represented by OR square, in which is in the red coordinate system, plus RP square, which is same as OQ square plus QP square. So, which is, so this is the first kind of behavior. There are some quantities which remains invariant, which means which does not change if you do a coordinate transformation. So, they are does not change under coordinate transformation. There are some quantities, for example, the position vector which has two components. So, x component and y component, and they do change. So, the components in the blue coordinate system and the red coordinate systems are different, but they are related by a simple rule that you take the components of the blue coordinate system, multiply by this rotation matrix, you will get the component in the red coordinate system. So, this is the behavior of the position vector under coordinate transformation. Now, I must be careful here. Now, I said here that the laws of physics should not depend on the choice of coordinate system. So, I have not mentioned which laws of physics, and if I really want to be rigorous at this point, I should mention what is the, I should take some laws of physics and demonstrate that this remains same under this coordinate system. But instead of that, I am going to take this approach that I will assume that laws of physics remain same under coordinate transformation, and then I will use this as a definition for a kind of a way to classify these two kinds of behavior. So, I will say that there are some quantities which behave as the distance between 2 points, in the sense that if you do a coordinate transformation, those quantities does not change, they remain invariant, and this type of behavior so those quantities are scalars. For example, if you take a object with some mass and then if you rotate the object. So, let us say if I take this rock and then if I rotate this, the mass, so each of this rotation is kind of a transformation, a coordinate transformation, but it does not change the mass of the object. So, mass is a scalar. Another class of material shows this kind of behavior. So, they have more than one components. So, note that this is a single number, this is a single number, one component. So, another class of material quantity that has more than one component. So, they are described by more than one number, but these components follow a certain rule. So, they the relation of the components in the blue coordinate system and in the red coordinate system, they has the same exact same relation, which means that suppose I take a quantity A whose components are A prime x and so let us say A x prime and A y prime. So, this is a component in the red coordinate system, and the same object has two components in the blue coordinate system. Now, if I do the same coordinate transformation, which means that I rotate the blue x axis of the blue system by an angle theta, then precisely the same matrix, the same rotation matrix. So, I have to use the same rotation same rule. I have to apply the same rule that you take these these components in the blue coordinate system and multiply by this matrix, same matrix. So, this matrix is exactly same as what we found when we looked at the coordinate transformation for the position vector, which means that they behave in the same way as the position vector. Since position vector has a sense of magnitude and direction, so these quantities are called vectors. They also have a sense of magnitude and direction and can be represented by an arrow. So, that is why we usually say that vectors are quantities which have both magnitude and direction. Now, using this way, so the advantage here is that using this method of classification, we can add more, we can easily scalable. So, this method is scalable. So, when you study, for example, engineering or even in science, you always try to find a method or concept which can be easily scalable or easily generalizable. So, this concept is easily generalizable in the sense that now we can define more complicated object quantities with more number of components, and which will. So, if I want to write down the components of, for example, a quantity like the stress or moment of inertia, we need 2 of this rotation matrix. Then we or we may need 3 of them, or we may need 4 of them using a particular certain format, which I am not going into. So, hence in general a quantity or any quantity that we will encounter in this course is classified as a tensor of rank n, where n represents that how many of this coordinate transformation matrix you will need to write down the relation between the components in the blue coordinate system and in the red coordinate system. So, if they are invariant, you do not need any you need 0 of them, that represents the invariant behavior, then these are scalars. If you need one of those coordinate transformation rule, coordinate transformation matrix, then these quantities are called tensors of rank 1. Now, in this course, most of the quantities that we will use or come across, they will be either scalars or vectors, that is tensors of rank 0 or rank 1. We will encounter only perhaps only one quantity, which is the moment of inertia, which is a more complicated object, and this is a tensor of rank 2, which means that if I want to write down the components of moment of inertia in the blue frame and in the red frame, then the components in the red frame are related. So, if I want to know the components of moment of inertia in the blue frame, then to calculate the components in the red frame, we need more 2 of this coordinate transformation matrix. So, this exact rule and how to write down these components we will discuss in due course as we progress in the course. Okay. Now, I want to mention a couple of comments on notations. So, the first thing, so this is based on my experience of teaching first year students the mechanics. So, usually you students do not pay enough attention when you write the symbols of the quantities, but this is a mistake. Why? Just trust my word that if you can write down a quantity correctly indicates that you have understood the concept well. It reflects how your level of understanding. So, second thing is this, if you pay attention to the notations, then it helps you to catch mistakes during problem solving when you are doing a calculation. So, here is a sort of very quick and review of about notations. So, my first point is that when you write down a scalar like mass, energy, power, etc., always remember to write units. It is very important. So, imagine a situation. So, as I mentioned before, why the units are very important, because as you know that there are different unit systems. So, for example, to give you a very simple example, so we mentioned that volume is a scalar. Now, in usually in India we use the metric system or SI units. So, we measure the volume in meter cube, cubic meter, or more commonly in liters. So, liter. So, 1 cubic meter is 1000 liter. So, let us say you have a kind of vehicle and you are trying to fill the tank with oil. So, if you go to the petrol pump, then you will ask for the amount of volume of oil in liter. But in other countries, for example, in US, they use a different unit system. So, they use something called gallon, and 1 gallon. So, if you go to the petrol pump in US, you will ask to fill your car with gallon, and in gallon is not same as liter. In fact, it is bigger than in gallon. Now, imagine instead of car, you have a aeroplane which is flying from India to US, and imagine that this is a non-stop flight, and suppose your job is to fill the tank of the aeroplane with oil, and suppose you know the tank capacity is something like, for example, let us say 1 lakh, and say that you do not remember, and what is the unit, is it 1 lakh liter or 1 lakh gallon. And so, if you do not pay attention and you assume that since you are in India, it must be 1 lakh liter. So, you fill the aeroplane with 1 lakh liter, but suppose the pilot who asked you to fill the tank with oil is from US, and he meant 1 lakh gallon, which is actually much greater than 1 lakh liter. Then what will happen is that when the plane starts to fly, it does not have sufficient amount of fuel inside the tank. So, it may have a danger of running out of fuel in the mid-air, and that all it happened because if you do not pay attention to the unit, and this, as you can see, that this is a very dangerous situation. So, always try to remember, write the units. Second is about the notations about vectors. So, I would like to summarize the different ways to write vectors. I am sure some of you or maybe all of you have come across this in your high school curriculum. So, the most so this is for for the types of notations that will be used in this particular course. So, the most common type of notation is to represent. So, take the vector as a momentum, which is a vector, it has a magnitude as well as a direction. Now, we can write this as a, so P represents the momentum with an arrow on the top. So, this indicates that this is a quantity that has a magnitude as well as a direction. Now, if you read the textbooks or even sometimes when in this course also, the vectors are denoted by boldface. So, this is a vector. So, this is a boldface. So, there is a dark thick color. So, this is a vector. Then sometimes these vectors are represented in terms of the components. For example, in 3-dimensional space, the momentum has 3 components, you need 3 independent numbers to describe momentum. So, these numbers are, let us say, the x component, y component and z component. So, they are denoted by px, py and pz. Now, as we have seen in today's lecture, that the third way of writing the representing the vectors are as a column vector. So, in this case, so this is also representing the components of the vector. Now, this in modern days, this third way of writing, I mean you can write it in a row vector or column vector. So, both will be used in this course, but the point is that in these days some of you or maybe all of you have learned some amount of programming, and in programming you may have come across the concept of array. So, an array is a variable with more than one component. So, an array behaves in many situations like a vector. So, this way of representing the vector as a row vector or column vector is kind of very useful when you writing some program and doing some calculation in computer. Especially some of you may be interested or may have also learning about kind of data science or data analysis. So, there when people represent a very complicated object with many different components. So, this is I am talking about an example which goes beyond the usual realm of physics. So, usually in physics the number of components is determined by the dimension of the space, whether in a plane you need 2 numbers to describe a vector, in this room you need 3 independent numbers to describe a vector. But in like in the example that we discussed before about the fruit in a basket, you can come across in real life situation a very complicated object. In order to describe that quantity, you need many different components. When I say many, I mean that it could be even hundreds or thousands, even millions or even billions of components. So, those kind of quantities, so those can, for example, it can be useful to describe, for example, a medical record of a patient and so on and so forth. In those cases, this notation is array, thinking of the vector as an array of numbers or a column of numbers or a row of numbers is very useful. Thank you.